Okay, since I have a weak acid that's being added to this, it's going to change things up quite a bit. So let's say that I have hydrofluoric, just because it's the easiest weak acid to write, and I'm going to titrate that. My titrant that I will use will be sodium hydroxide. Okay, and as I said in a later video, I'll do the actual numerical calculations. Right now we're just looking at the logic of what's going on. Alright, so right now in the beginning, my species that I have present, before I add any of the sodium hydroxide, what I have in that solution is HF and water. Right? I just have the hydrofluoric. It's a weak acid, so it doesn't dissociate to any great degree, so I keep it like this. This is with no sodium hydroxide added. Okay? So the milliliters equal 0. Okay? Well, since I have hydrofluoric acid, this is a weak acid, this is going to be just your traditional weak acid problem. You're just going to take your concentration of whatever the weak acid is in the container, plug this in, solve this here, and you end up with just doing a simple ice table, okay, and then a Ka. I'm not going to do this, of course, and you would solve for X, which is equal to hydrogen concentration, and find your pH. Typical problem that we've been doing so far. Nothing different here. Nothing different here. So that's what you do in the beginning. Now, after you add the first drop, okay, so when the volume here, when the milliliters is now greater than 0, what we create is a buffer. We're going to create a buffer. Okay, why is that? Well, let's take a look at what happens to see why a buffer forms. Let me erase this. Okay. So after adding the sodium hydroxide to the hydrofluoric acid, let's take a look at the species that we have present. Well, we have hydrofluoric acid, we have water, and what we're going to do is we're going to add sodium ions and hydroxide ions. Okay? So what I have, what's going on here is I'm going to have an acid. Again, how do I know? I'm just identifying what I have. I have an acid here. Water's neutral. It's going to have it will do something. So please be patient. It will do something. The sodium ion, and then the base. Okay, so I've got a weak acid and I have a strong base being added, so of course these two are going to react together. Acids react with the bases. So hydrofluoric acid is going to react with OH minus. Now as soon as I introduce OH minus, as soon as I add hydrogen ions, that means that there is no equilibrium. So whenever you see these strong acids, strong bases added to the solution, no equilibrium, we're going to use a BCA table. This should be very familiar to you from the stuff that we did with buffers. So this makes water, and look at this, it leaves behind the fluoride ion. Originally all I had in here was hydrofluoric acid. When I finish this, okay, I'm going to have some of the acid here, I'm going to have some base here. These are going to change by X and change by X and go up by X and go up by X. Well, initially this is going to run out. This will be our limiting reactant. So here we're going to have some of the acid left over, and we're going to start to create the base. Right? So our base is going to go up. So what happens is our concentration of the acid goes down, and the concentration of our anion goes up in these reactions. So we start to see that after we've added the first drop of base, what we're left with afterwards. Now if we think about listing the species that are left over, what we have left over is HF, hydrofluoric acid, still have that water there, and we still have sodium ions. But now what we've introduced are fluoride ions. And that should ring a bell for you. That should hopefully indicate, here I have an acid, and I have a base, and you could say, well, wait a minute, won't they react together? Well, I guess you could say that, but they're conjugates of each other, right? If I have a weak acid and a conjugate base of the weak acid, this is your buffer. So what I have done is I've buffered my own solution by doing this. And this is going to have a big impact here. Okay? So now to find my pH, what I do is I take the results of this, what I have is an after, and as an after, and I plug that into the ice table. Now you guys know better than that at this point. What you can then do is use, instead of the ice table, you can use the Henderson Hasselbach equation. Right? So if you have a buffer system, you can start using the Henderson Hasselbach equation. This cannot be used at the first drop. Okay? It can only be used once the buffer is established. Okay? All right, so we've got the basic idea. Now what's going to happen is this is going to keep going on. I'm going to keep adding more base. I'm going to add some more base to this drop by drop by drop. And every drop that I add is going to add more and more and more. And eventually, this is going to run out and this is going to run out. You're going to get to the point where they both get to what's called the equivalence point. And as that happens, this gets lower and lower and lower while this gets bigger and bigger and bigger. Okay? So let's take a look at what the titration curve would look like. Okay, so if we have the volume of the sodium hydroxide being added here and my pH here, okay, it's going to look kind of like the same curve that I had. It's going to have this distinct curve here, and this going up and then going like this. Okay? Now, when we look at this curve, a number of things are going to happen along this titration curve. A couple key points. First of all, in the beginning, at volume equals 0. No buffer, and you cannot use Henderson Hasselbach. So no Henderson Hasselbach at that equation. Only thing you can use there is the ice table. So it's just a weak acid, just a simple weak acid problem. That's it, weak acid calculation. Okay. Now as you go along here, think about what's happening in this reaction. Let's write the reaction down here again. H fluoride, right, reacting with the OH minus, okay, what it's going to do is it's going to keep creating water and HF minus. Now this starts off as 0. If I use the BCA table here, okay, so let's say that this was, just say for, make it easy, let's just say it's 10 molar, 10 moles here. All right, if I originally add 5 moles here, this is going to go down by X, this is going to go down by X, this is going to go up by X, and up by X. Well, this is going to run out and go to 0. Isn't this going to go to 5 moles here? And this is going to go to 5 moles. Right? As this number gets bigger and bigger and bigger, my amount of acid is going to keep getting smaller and smaller and smaller, and therefore my pH is going to keep going up because I keep getting more of the acid, or I'm sorry, more of the base. You can also see this in the Henderson-Hasselbach equation, right? pKa plus the log of the base over the acid. As the base gets greater, your pH starts to get greater. Okay, well at this point here, if these two are the same, hopefully remember that that's called an optimal buffer. It's an optimal buffer. And that point is going to be what's called the halfway point of our titration. I'm going to say that goes right here. That's what's called the halfway point. Halfway point. And this is where you have an optimal buffer. And at this point here, you have the pH is equal to pKa. Remember we talked about that before. pH is equal to pKa. That happens right here at this point, at that halfway point. Now again, you're going to have an equivalence point, and that equivalence point is going to be, you know, another half of that way from there. So that's why this is the halfway point, because you're halfway finished. Why? Because you're going to take out the other half of this and make this go to 0. So let me show you that part. So if I continue to add the hydroxide, I'm going to get to a point where these are both going to be equal to each other. This will drop out, and this is going to go to 10 moles. Okay? That is called the equivalence point. That's your equivalence point. We call it the equivalence point because our acid and our base are at equivalence to each other. The strong acid, the strong base that's added is equivalent to the amount of moles of the hydrofluoric acid. We don't want to call this a neutralization point. Absolutely don't want to call it neutralization. So let me explain why. Let's think about the species at this point when we get to the equivalence point. So we get to the equivalence point. What are the species that we would have present at that point? Okay, the hydrofluoric is gone, OH is gone. Well, we have water, that's definitely there, and we know that we have that sodium ion from the hydroxide, and what's left behind is that fluoride. So what's going to happen here is that fluoride ion is now going to react with the water. So at the equivalence point, you have hydrolysis of a salt. you're going to have that hydrolysis of a salt occur. So what that means is that fluoride ion is going to react with the water, and you're going to end up having a reaction equilibrium where this forms HF and it forms your OH minus. So it's going to make it basic. Did everybody see that? Hopefully you can kind of see what I'm talking about here. At the equivalence point, because I have that fluoride ion left over and it's a conjugate base and it's effective and it's going to take that hydrogen ion, it's going to create a base. So when we get to the equivalence point here for this, our equivalent point is basic. So this is going to be greater than 7. So our pH of 7 is here. This actually crosses over above 7. Hence why I hate calling this a neutralization point or a neutralization reaction, because actually at equivalence we have a basic solution. And again, you can do the ice table here, right, to figure this out. You can no longer use the Henderson-Hasselbach equation, because in this region here, from right here all the way through here, right before that point is where you have the buffer. So here's where you have your buffer. And what you can do there is you can use the Henderson-Hasselbach equation for this whole section. Okay. At this point here, at this red point, you have to do hydrolysis of salts. Okay, it's hydrolysis of salts. Now if I continue on and I make this 11 moles, by adding a little bit more, this now becomes excess. And now, if this is my excess reactant, what that means is I have a strong base dominating the rest of this problem. And the rest of this here becomes strong base. Okay? So that's kind of a breakdown of a weak acid strong base titration. Now, wanted to go into the third type, but I think I'm going to have to hold off just because I know you're going to get upset with me because this video is already way too long. So I'm going to stop here and I'll do the weak base strong acid titration in a second video. Alright, thanks a lot guys. I'll see you later.